All right, good morning. So we're going to talk about 7.3 today, and pretty much this is what we've been doing for 7.2, just more of it. Okay, so here we go with that. Actually, I need to know where is my Laplace transform table. Okay, right there. Okay. All right. And again, this is going to be something that you are going to have access to. So don't stress over, I've got to memorize all of this, because you don't. Okay. Let's not use a Sharpie on my computer table. Let's use the pen it came with. Okay, so the first thing to talk about is that there's a little bit of theorem, and they offer this without proof, so I'm not going to go through proving it. Part of it we can prove this one, right? This would be e to the at f of t, the Laplace transform of this is equal to the Laplace transform of just this function, right, with a translation, s minus a, okay? And the inverse Laplace transform, all right, of f minus a, okay, is equal to e to the at f of t, this f. Okay, so we just find, if we just restrict ourselves to like having to know like polynomials, sines and cosines, and maybe you know, other exponentials, maybe some hyperbolics, this will work out real well for us. And I'll give you a clue as like where should I be looking. Okay, so I'm going to do this two ways. I'm going to show you how they want you to do it in the book first, and then I'm going to also just show you on the table. It doesn't really make that much difference to me which way you do it, because I'll never be able to tell how you actually did it. Okay, so here we go with that. All right, so the first example we have here, okay, is we have to find the Laplace transform of t cubed e to the negative 5t. Okay, and what we're going to do is we're going to say, well, this is e to the negative 5t times t cubed, right? So what is the Laplace transform of just t cubed? Right? That's going to be, or t to the n even, it's going to be n factorial over t to the n plus 1, or s rather, s to the n plus 1. Okay, so yeah, let's clean that up. Okay, and I just got that off of the table. Okay, so it's not like, you know, you're never using the table for this, but if you wanted to memorize like a small subset, polynomial will be good. So the Laplace transform, right, of t to the n is equal to n factorial over s to the n plus 1. Okay. So in this case, if I have the Laplace transform, right, of t cubed, let's go ahead and just a little bit. Okay. Laplace transform of t cubed, that is going to be 3 factorial over s to the 4th. Okay, 6 over s to the 4th. All right. So what we're going to do, because we have this t, or this e to the negative 5 plus t, this is really, right, what we're going to do is we're going to do Laplace transform of t cubed e to the negative 5t. Right, this is the Laplace transform of s plus 5, where f is this function. Okay, that's f, is t cubed. So all we're going to do here is we're going to say this is 3 factorial, right? 3 factorial over, instead of s, we're going to replace it with s plus 5 to the 4th. All right, that's it. Now, let me show you. Okay, so we're just going to do a part B here. So if I just have Laplace transform of t cubed e to the negative 5t, okay, let me just show you it this way. So we're just going to look here, okay, and we're going to find, where are you? T times e to the t. No, I wrote these down. There we go, 23. Okay, so look at 23 and say, okay, t to the n is equal to n factorial, and then s minus a to the n plus 1 factorial. Okay, so from problem number, or from table item, right, number 23, right, this says t to the n e to the at, the Laplace transform of this, right, this is equal to n factorial over s minus a to the n plus 1. And you can read it right off of here. Okay, so that's still going to be, right, if I plug in my t cubed e to the negative 5t, that's going to be a Laplace transform. Right, that's going to be 3 factorial over, and then here we have s plus 5, right, that's my s plus 5, and then to the 4th power. So we get exactly the same thing. That's exactly how they generated these values very quickly. But you're allowed to use this table in order to do this. So this might give you a little bit of a place of where to look or how to maybe to do it. Maybe you don't need the table all the time, but you always have it with you. So if you wanted to check just in case, go right ahead. Right? Maybe a harder example here. So if we want to do Laplace transform of 1 minus e to the t plus 2e to the negative 4t, parentheses, cosine of 3t, okay, and do this Laplace transform. Okay, so the first thing we got to do is we're really going to distribute this cosine 3t to each of the every terms in here. Okay, that's just what we're going to do. So this is the Laplace transform, right, of cosine 3t minus e to the t cosine 3t plus 2 e to the negative 4t cosine 3t. All right. And if I go through, let's see here. If we go through and look at this, table entry number 8, see this one I wrote down, that's our cosine. Okay, that's our cosine of AT. Okay, so I'm just going to do this for just a moment. Okay, I'm going to say, well, this is going to be f of, right, f of s. Okay, this is going to be minus f of s, oh, minus 1. Okay, f of s minus 1 minus 2f, this is s plus 4, right, because it's minus, so it's minus minus. Okay, and let's just go ahead and do it that way. All right, and again, we'll do it just by the table in a moment, but my cosine is s, right, s over s squared plus a squared. Okay, s over s squared plus a squared. A is the, right, is the coefficient there. So we're going to have s over s squared plus 9, okay, minus, and then here's s minus 1, right? So instead of that, we're going to have s minus 1 over s minus 1 squared plus 9 minus 2, right? And this is going to be s plus 4. So we're going to have s plus 4 over, parentheses, s plus 4 squared plus 9. Okay, and all I'm doing is kind of replacing my s with s plus 4's s minus 1's. Okay, now if you use it, well, I'm not going to memorize anything more than I have to, but that's fine. Okay, so check it out. We have, right, let's work down which ones they would be. So if I look at table entry number 20, right, they tell you, here's e to the at, s minus a, cosine bt, s minus a squared plus b squared. Okay, you know, I'll be an obnoxious math teacher and say, you know, the check is left to the reader. Okay, but I think it's pretty easy to see that if we applied this table entry, right, to this function, to this Laplace transform here, you would get exactly the same thing. Okay, so that's what they're calling attention to as they're doing it. And that's how they kind of want you to go through and deal with how to do it. Personally, you know, this was not something that I actually learned in my IDE class. We just used the table, and I get along just fine. So it's neat to see it. It's like, oh yeah, that does work pretty well. So that's kind of cool. But it's not something that's like required, because what did we do to figure out cosine? We looked at the table. So yeah, I won't be testing you on that particular skill. It's just going to be kind of nice to not have to look things up all the time. Okay. And again, it might give you a better place to look. It's like, well, I've got some e's. I don't got to look at the e's so much, right? I got to look at where the cosines are. Okay. So the next one is repeated roots. Okay, so I know that all of you absolutely love doing partial fractions and all remember how to do them perfectly. And the ones that they had before, even the long one, even that you know, third order DE was kind of tame in comparison to what you could get. So what we're going to do here is I want to find the inverse Laplace transform of 4s minus 1 all over s squared s plus 1 cubed. Okay. And there is no like, well, maybe I could let, you know, s minus 1 here. That's going to be, no. Okay. There's a times in here, so you cannot pull them apart this way. You can pull apart the pluses, but you can't pull apart the times. Okay, so if you wanted to do two partial fraction problems by breaking this up, that's fine. I would not recommend that. Okay, so what we're going to have to do is a giant partial fractions problem. Okay, so this is everything you've always hoped for when you learned about partial fractions in pre-calc, and this is the best problem you could ever get. So we're going to break this apart. So that's an a over s plus a b over s squared plus a c over s plus 1. Remember, repeated roots, repeated values. This is still linear, so we repeat it, but since it's still a linear term. We just have the linear coefficient on the top. Same thing is going to happen here, right? We have a c over s plus 1. The fact that we have repeated means that we don't change the format for what's going on in the top. We just repeat them. Okay, and I can hear you now saying, you got to be kidding me. You want me to do 5 equations, 5 unknowns? Yes. No. This one, what we're going to do is we are going to use a combination of techniques here. We're going to use a little bit of the shortcut because it gets rid of a couple of things. And we're going to do some solving equations. Okay. So let's untangle this, right? We're just going to multiply. What we're going to do is we're just going to multiply by the least common denominator. That's going to be s squared s plus 1 cubed. That's going to knock this out. And it is actually going to knock out everything here. It's just that everything is going to have like its own set of combinations of what's going on here. All right. So this is going to be well, there's two s's here, one of them here. So we still have an as, and then I've got s plus 1 cubed. Right? How did I do this? Okay. Plus b, both the s squareds go, right? So we have s plus 1 cubed. Okay. Plus c, we have an s squared here, and then 1 of my s plus 1s gets used up. Plus d, we have an s squared here, and 2 of my s plus 1s are gone. Okay. And then plus e s squared is equal to 4s minus 1. Okay. So if you had pre-calc if you took the actual pre-calc rather than the advanced algebra rather, they showed you the binomial theorem, so you could multiply this out quickly. So this is going to be as s cubed plus 3s squared plus 3s plus 1. Okay, I'll just note this binomial theorem. If you go to look this up, this is taught anywhere from about 9th grade, 10th grade, maybe 11th, all the way up through graduate school. So if you find yourself a binomial theorem video and they're going off and about stuff that like, this is not something I ever dealt with, you're probably at the wrong level. Okay, they do teach this in some high schools. You can certainly find a high school level or college freshman explanation for binomial theorem. Okay, I'll leave that for you guys to do. Might put a link in there for Purple Math. Okay, so you can refresh your memory. It comes up often enough that it's real useful to remember that this exists. Plus b, okay, and then here we have s cubed plus 3s squared plus 3s plus 1. Okay, it'll be optional. I'm never going to quiz you on this again. If you want to take all the time in the world to multiply this out, you go right ahead and do it. Okay, plus c, and I've got an s squared here, and I've got s squared plus 2s plus 1. That's not a problem for anybody, I hope. Okay, plus ds squared s plus 1 plus es squared. Now I'm going to break this. I'm going to go ahead and distribute the s's in just so that I have a real clear accounting of what has to happen. So we're going to say this is a s to the 4th. Actually, keep this line in your memories. Okay, we're going to come back to that. And I have a 3s squared plus 1 is cubed plus 3s squared plus s. Okay, here's my b. S cubed plus 3s squared plus 3s plus 1. Okay, plus c. Okay, and that's going to be s to the 4th plus 2s3 plus s squared plus d s cubed plus 1 plus es squared. Okay. So we're going to come back to this because that's going to help us get our equation set up. But, oops, I don't want to do that. Okay. Let me go back up to this line right here. Okay, actually, I'll rewrite it. I wish I could copy it, but I don't know how to do that. Okay, so I've got an a s plus 1 cubed plus a b s plus 1 cubed plus a c s squared s plus 1 squared plus d s squared s plus 1 and plus es squared. This was equal to 4s minus 1. Okay. Now, what if set s equal to 0? Well, what's that going to do? It's going to knock out my e, my d, my c, and my a. The only term I have left, right, is going to be b. So in that case, we have a b, 0 plus 1 cubed, right, is equal to negative 1. Ha! 1 times b is equal to negative 1. So we've gone from 5 variables down to 4 variables. Okay, so we're not out of the woods yet, but at least we only have a 4 by 4 equation to deal with. Let's set s equal to negative 1. Okay, that's going to knock out a, b, c, d. We have e times negative 1 squared, right, is equal to 4 times negative 1 minus 1. So e is equal to minus 4 minus 1, minus 5. We are now down to 3 variables, 3 equations. Okay? That is a much easier sort of system to deal with, right? We don't have to deal with b and an e here because we already know what they are. Okay, now I'm going to go ahead and equate coefficients. Okay, so looking by a quick inspection here, what is my biggest values? It looks like s to the fourth, that's our biggest one. So let's look at s to the fourth. Okay, and let's pull out everything that has s to the fourths in it. So we have an a and a c. So we have a plus c is equal to 0. There's no s to the fourths on the right-hand side. Okay, my s cubed term. Okay, there's a few more of those. We have 3 a's. Okay, plus a b. B was -1, right? C, we have a plus 2 c's, right? Plus 2 c's. Okay. We're on s cubes, right? So we have a plus d. And there were no s cubed terms on the other side. Okay. S squared. Okay, we have 3 a's. All right. Let's see, we have 3 b's, right? Because that's squareds. So we have 3 b's. B was -1, remember? Okay. We are on s squared, so we have a plus c. Again, we're on s squareds. Did I mess a d up? I did. D should be s cubed plus s. But we didn't have a d, right? We don't have a d. Because we just have s squared. Oh, we have an e. What the heck was e? E was -5. What's on the other side? How many s squareds we have? None. We have s. Okay, what about s? What's going on there? There we go. So I just want single terms. Okay, so I've got an a -3. That's my b, right? So there's one b term for constants. There were no c, d, and e terms. What on the other side? It's 4, right? Because it was 4s plus 1 all the way back up here. 4s, or 4s minus 1 rather. Okay. And then my constant term. Okay. And I think the only constant term I have was b, and b was -1. And then on the other side, what was it? -1. Okay, so that's a nice tautology there. Okay, so I think we could say here that a is equal to 7. We are now down to 2 variables, 2 equations. Okay, this is a very doable, right? This is a very graspable sort of a system. It took a while to set it up, but it turned out that this really wasn't that bad. And since we know from 1, right, this first equation that 7 plus c is equal to 0, right? I think c would be -7. So all we need to do is just plug our values into one equation, and then we're going to get d. Okay, so when I first saw this, I was like, oh, this is going to be, I'm going to be getting the calculator out. That's how we're doing it. And then I started taking it apart, and I was like, oh, wow, somebody came up with a really nice problem for us to do. It's your choice. What do you want? Oh, no, we don't. We only have one d, don't we? Oh, there should have been one here. As okay, my s term. There should have been a plus d here. No, it shouldn't have been. Oh, yes, there should have been. Yeah, there should have been a plus d. My constant, my. All right. Let me not do that then. We still get s of 7, area 7, but. All right, I believe we have a plus d here. Yeah, we do. All right. Oh, no, it's a cubed and then squared. Okay, no, I was right. I was right. Squared term. There's the plus d. Okay, there it is. Okay, missed it. This one isn't there. So a is still 7. Okay. But we have a d here, we have a d here. Cubed and squared. Your choice. Doesn't matter which way you do it. Okay. So if we have 3 times 7, picking the s cubed term, right? So we have 3 times 7 minus 1 plus 2 times negative 7 plus d is equal to 0. So we have 21 minus 14 minus 1 plus d is equal to 0. 21 from 14, that's going to be what? 7. 7 minus 1 plus d is equal to 0. Aha, d is equal to negative 6. What if you like the other one? Besides, problem like this, a lot of places we could have screwed up. Let's go ahead and double check. So we have 3a, 3 times 7, okay, minus 3, minus 7, because remember c, right, was negative 7, plus d, minus 5 is equal to 0. Right. So what do we have here? We have 21. What do we have? 10, 15 here. 21 from 15. I think that's 6, isn't it? Okay, pretty happy about that because I didn't screw up the arithmetic. What were we doing? Oh yeah, this is a giant partial fractions problem, wasn't it? Again, this is a lousy quiz question because look how many steps we have to deal with and how many places are there to mess up. And yeah, so let's just pull this apart, right? We have a squared. Okay, so what do we have? Over down here, we have, going back to where my original partial fractions, right? Actually, I'll just write it down. We have a over s plus b over s squared plus c over s plus 1 plus d over s plus 1 squared plus e over s plus 1 cubed, right? That was our first thing. And we're going to say that a is going to be 7 times 1 over s plus b. B was negative 1 over s squared plus c. What was c? C was negative 7 1 over s plus 1. D was negative 6 s plus 1 squared. Okay, and then e was what? Negative 5? Was e was negative 5. Good. Minus 5 s plus 1 cubed. Okay. Now here's where this f of s minus a, right? Inverse Laplace transform was f of t. Because this s plus 1, this s plus 1, this s plus 1, I know these are just, right, or e to the at rather. I know these were just polynomials, right? And this s plus 1, this s plus 1, this s plus 1, this is just going to be like e to the somethings with the polynomials, okay? E to the negative t's, the polynomials. So 1 over s, that was just 7, right? S squared, that's going to be minus t, okay? And then minus 7, and then this s plus 1, right? This is just a constant with e to the negative t here, okay? Minus 6, and then squared, t, e to the negative t, okay? Minus 5. This is going to be t, oh, not quite, because I need a 2 factorial and a 2 factorial here, right? So we have 5 over 2 to pull this around. And then we have 2 factorial over s plus 1 cubed. So that's going to be e, or it's going to be t squared e to the negative t. Right? And there is our answer for that. Okay, so that's how you do those. They're delightful. Okay, actually, really, this one really wasn't that bad. So I'll take it back. If I gave you a problem like this, okay, there's still a lot of moving parts, and I would be unlikely to give you a problem like this. But at the same time, I don't think I'd lose too much sleep if I ended up giving you a problem like this. Okay, because it did all break down. So if it tells you, like, you know, here's a 5 by 5 set of equations, like, there's going to be a hint, right? Use your calculator. But if there isn't a hint, you can expect something like this. A whole bunch of this stuff is just going to fall out, and you're not going to get like this huge problem. Okay, this has probably gone on long enough, so I'm going to go ahead and stop this one, and then we'll pick it up and do something in the next time.